This paper provides a comprehensive review of theoretical results obtained from the three-dimensional equations of anisotropic elasticity or piezoelectricity for waves and vibrations in quartz crystal plates. It covers both classical results on acoustic wave resonators and their relatively new applications in acoustic wave sensors. The paper begins by discussing the basics of a quartz plate, including its material matrices and governing equations for displacement vector and electric potential. These equations are derived from the three-dimensional equations of linear elasticity or piezoelectricity, which are fundamental for understanding and designing quartz crystal plate resonators and sensors. The paper then delves into the simplest thickness modes, considering various complications such as mass layers, contact with fluids, and air gaps. It also explores more complex transversely varying modes, including shear horizontal modes and straight-crested modes varying along the diagonal axis of rotated Y-cut quartz plates. The paper concludes with a summary of the key findings and implications for the design and optimization of quartz crystal plate resonators and sensors. The equations presented in the paper are essential for understanding the behavior of quartz plates under different conditions. For instance, the equation 1 describes the relationship between displacement vector, electric potential, and their derivatives in a monoclinic crystal like rotated Y-cut quartz. Similarly, equation 2 represents the relationship between electric displacement and electric field components. These equations form the basis for analyzing the performance of quartz resonators and sensors. The paper highlights the importance of considering anisotropy and piezoelectric coupling in the analysis of quartz resonators. This is because these factors significantly influence the vibration and wave propagation characteristics of the plates. By employing approximate two-dimensional theories derived from the three-dimensional equations, researchers can model vibrations of piezoelectric plates and apply them to the analysis and design of quartz resonators. The paper also emphasizes the role of different cuts of quartz plates, such as the stress-compensated SC cut and the widely used AT cut. These cuts have different material matrices and exhibit varying properties, making them suitable for various applications. For example, the AT cut is known for its high stability and low temperature sensitivity, making it ideal for timekeeping and frequency operation. In conclusion, this paper provides a systematic review of theoretical results from the three-dimensional equations of anisotropic elasticity or piezoelectricity on waves and vibrations in quartz crystal plates. It covers both classical results on acoustic wave resonators and their relatively new applications in acoustic wave sensors, making it a valuable resource for researchers and stakeholders in the field. Here is a combined summary of pages 3 and 4 of the research paper. The analysis of quartz plates involves a complex system of partial differential equations, further complicated by boundary conditions. However, for frequency analysis, the small piezoelectric coupling can often be neglected, and an elastic analysis is sufficient. This simplification is useful for understanding the basic frequency behavior of the structure. Nevertheless, an electrically forced vibration analysis including piezoelectric coupling is necessary for simulating a crystal device as a circuit element. Thickness modes in a rectangular quartz plate are considered, assuming the length and width are much larger than the thickness. Pure thickness modes depend on the plate thickness coordinate and time only, and can be decoupled into two groups of equations. For time harmonic motions, these equations become linear ordinary differential equations with constant coefficients, making them mathematically solvable. The thickness shear mode in the x1 direction, governed by equation 4, can be conveniently excited by a thickness electric field through the piezoelectric constant E26. The distribution of the thickness shear deformation in modes along the plate thickness is shown in Fig. 3. The fundamental mode with n equals 1 is commonly used in devices. When resonators are subjected to environmental effects, such as temperature changes, stress, or additional surface structures, the resonance frequencies of the thickness shear modes change, providing the foundation for resonator-based acoustic wave sensors. One such sensor structure involves attaching a thin layer of another material to the surface of a crystal plate, which lowers the thickness shear resonant frequencies due to the inertia of the mass layer. This effect has been used to make quartz crystal microbalances for mass sensing. The sensitivity of a QCM is given by the Sauerbrey equation, which treats the mass layer as a change of the plate thickness. Piezoelectric solutions for thickness shear vibrations of plates with mass layers have been obtained, and mass sensitivity can also be obtained from a perturbation integral. Theoretical analyses of thickness shear (TSH) vibrations of crystal plates with mass layers, fluids, and particles are discussed. Imperfect bonding between the mass layer and the crystal plate can lower or raise the resonance frequencies of resonators under certain conditions. The shear modulus of the mass layer may also have a role, especially when the mass layers are not very thin compared to the crystal plate. An effective mass layer inertia, which is frequency dependent, can be introduced to account for interface elasticity or thick mass layers. The effects of fluids on TSH vibrations are also examined, including the use of fluid sensors to measure fluid viscosity or density. The classical result for frequency shifts caused by a fluid in contact with an elastic plate is presented, along with subsequent studies on fluid layers on crystal plates, electrodes with finite thickness, and multilayered structures. Other effects, such as particle loading, fiber loading, and angular rate, are also considered. Particle loading can raise or lower the frequencies of the plate, while fiber loading can be used to measure fiber properties. Angular rate can affect the resonance frequencies of a TSH resonator, making it suitable for gyroscopes or angular rate sensors. The paper also discusses X3-dependent modes, which are necessary due to the finite size of real devices, where edge effects are present and pure thickness modes cannot exist. The shear horizontal, shish, or antiplane motion is described, governed by equations 5 and 6, which are simpler than equation 2. Shish motions include face shear, Fs, and thickness twist, Tt, modes, with dispersion curves shown in Fig. 5. Elastic and piezoelectric solutions for these waves were obtained, along with studies on mass layers, interface elasticity, and thick mass layers with shear elasticity. In the context of quartz crystal microbalances, QCMs, and surface acoustic wave (SAW) devices, the interaction between flexural and shear elasticity with mass layer inertia plays a crucial role in determining wave frequencies. This interaction can either raise or lower these frequencies, as observed in studies on waves in a quartz plate on an elastic half-space, 52. The effects of a viscous fluid on flexural and thickness shear waves were also investigated, 53, while waves in a plate with non-uniform material properties were studied in 54. Moreover, the case of a QCM carrying a porous mass layer was analyzed in 55. Frequency spectra for shish vibrations of a finite plate have been generated, 56, showing resonance frequencies versus the aspect ratio of the plate. These spectra revealed two families of curves, one representing flexural-dominated modes and another for thickness shear-dominated modes. Strong coupling between these two types of modes occurs when the flat parts of the TT family begin to bend or intersect with the FS family, which is undesirable in device operation and should be avoided. Energy trapping and Beckmann's number are key concepts in understanding the behavior of partially electroded crystal plates. Energy trapping refers to the phenomenon where vibration energy is confined mainly under the electrodes and decays exponentially away from their edges, as demonstrated by the trapped modes in a partially electroded rectangular resonator, 60. Beckmann's number, derived in 58, is the ratio of the electrode length over the plate thickness below which only one trapped mode without a nodal point in the X3 direction exists. Trapped thickness shear modes were studied in 57, 58, with Beckmann's number given in 58. For a T-cut quartz plates, exact solutions over finite domains can only be obtained for a plate with a pair of slightly tilted edges, 59. Neglecting the smaller elasticity constant C56, a series of useful elasticity problems over rectangular domains become solvable by trigonometric series. This approximation is particularly useful for understanding the behavior of partially electroded rectangular resonators, 60. Where one of its trapped modes is shown to have oscillatory behavior in the electroded central region and exponential decay away from the electrode edges. The research discusses various aspects of resonator manufacturing, particularly focusing on the effects of electrode size on energy trapping in finite plates. It highlights the challenges in modeling due to electrode mismatch and the need for piezoelectric analysis. The study also explores different resonator structures, including a mesa resonator with stepped thickness, and their performance in terms of energy trapping. The importance of mass layer non-uniformity and imperfect bonding is emphasized, as these factors significantly affect frequency and energy trapping. The governing equations for straight-crested modes with in-plane variations are presented, illustrating the complex coupling between variables. The discussion also touches on propagating waves in infinite plates, including their separation into symmetric and antisymmetric waves, and the long wavelength limit, which approaches Cauchy's equations. The research provides a comprehensive overview of the technical challenges and opportunities in resonator manufacturing, highlighting the need for detailed analysis and experimentation to overcome these hurdles. Here is a combined summary of pages 11 and 12 of the research paper. The dispersion relations for flexural and flexural shear (FS) motions are derived, and their corresponding dispersion curves are shown in Fig. 11. These curves are local approximations of the dispersion curves for long waves and low frequencies. The extensional motion is symmetric and its dispersion curve is not shown in Fig. 11. The paper also reviews other results, including the propagation of straight-crested waves along the x1 direction in a quartz plate with symmetric electrodes, and the analysis of waves in a doubly rotated cut quartz plate exhibiting monoclinic symmetry. Additionally, piezoelectric solutions of straight-crested waves propagating in a plate of triclinic crystals are obtained, and dispersion curves for AT-cut plates are presented. For AT-cut quartz plates, the relatively small elastic constants 14C, 24C, and 56C are neglected, and the equation of motion splits into two groups. One for the FS and TT waves, and the other for coupled TSH and flexural waves. The dispersion curves for straight-crested waves governed by the simplified equation are obtained, and solutions of finite plates using approximate boundary conditions in integral or resultant form are presented. The paper then discusses modes depending on both x1 and x3 directions, where the problem is 3D and theoretical solutions are impossible unless some approximations are made. The major displacement component is U1, and the corresponding equation is derived. This equation is solved for a rectangular plate resonator, and analytical solutions for contoured resonators with quadratically varying thickness for strong energy trapping are obtained. A solution to the equation in terms of trigonometric series for a partially electroded resonator is also given, showing the energy trapping effect of the electrodes. Finally, the paper concludes that the 3D piezoelectric equations for quartz plates and various versions of their approximations, as well as solutions of different models, provide fundamental understanding of the behaviors of resonators and acoustic wave sensors. These results are applicable to langasite and other crystals, and serve as benchmarks for various approximation techniques, analytical or numerical. This paper presents a comprehensive analysis of the thickness shear vibrations of piezoelectric plates, particularly focusing on the effects of surface loadings in liquid environments. The study begins by discussing the thickness shear vibrations of piezoelectric plates with various types of surface loadings, such as particles, beams, and hemispherical units. It then explores the impact of these loadings on the frequency shifts of the quartz crystal resonators in thickness shear modes. The authors also delve into the effects of couple stresses and strain gradients on the vibrations of the piezoelectric plates, providing detailed mathematical models and equations to describe these phenomena. Furthermore, they examine the interactions between the quartz crystal resonator and an array of microbeams or hemispherical substance units immersed in a liquid, shedding light on how these interactions influence the frequency shifts of the resonator. The paper also touches upon the transient thickness shear vibration of a piezoelectric plate of monoclinic crystals, as well as the phase shear waves in rotated Y-cut quartz plates. Throughout the paper, the authors draw on numerous references from previous studies to provide a thorough understanding of the subject matter, making it an invaluable resource for researchers in the field of piezoelectric vibrations and quartz crystal resonators. The paper presents a comprehensive analysis of thickness shear and thickness twist vibrations in quartz crystal plates, focusing on the effects of mass layers, electrodes, and other factors on these vibrations. It discusses various aspects such as energy trapping, dispersion relations, and resonant frequency functions for rectangular crystal plates. The study also explores the impact of imperfect bonding and non-uniform mass layers on quartz crystal microbalances. The authors have utilized several mathematical models and theories, including the work of Mindlin, Eckstein, and Tiersten, to understand the behavior of these vibrations. They have also cited numerous studies on the subject, demonstrating a thorough understanding of the existing literature in this field. In particular, the paper highlights the importance of considering the monoclinic symmetry of quartz crystals when analyzing their vibrational modes. This is crucial for accurately modeling the behavior of these materials, which are widely used in electronic devices due to their piezoelectric properties. The study's findings contribute to the development of more precise models for predicting the vibrational modes of quartz crystal plates. These models can be applied in various fields, including sensor technology, where the ability to accurately detect changes in mass layers is essential for sensing applications. Moreover, the paper discusses the effects of electrodes and their placement on the quartz plate, as well as the impact of fluid loading on the vibration modes. This information is vital for the design and optimization of quartz-based devices, such as quartz crystal microbalances and filters. The research concludes by emphasizing the need for further studies on the subject, particularly in terms of experimental verification of the theoretical models presented. It also suggests that the techniques developed in this study could potentially be applied to other types of piezoelectric materials, expanding the scope of the research beyond quartz crystals. Overall, the paper provides a detailed exploration of the complex vibrational behavior of quartz crystal plates, shedding light on the intricate interplay between various factors and their effects on these vibrations. The findings presented here have significant implications for the development of more efficient and precise devices utilizing quartz crystals.